Good day, everyone. My name is Danso Kelvin Ocho, and today I'll be talking about a key technique used in a cache memory organization. That's the fully associative mapping. And this is an important concept in a computer architecture, especially when it comes to the speeding up memory access and improving CPU performances. So when we talk about cache memory, we say a cache memory is a small and a fast type of memory that sits between the CPU and the main memory. And its job is to store a frequently used data so that the CPU can access it quickly. When the data needs to be loaded into the cache, the system must decide where to place it. And that is where the mapping techniques works in. And there are three main types of this technique, namely the direct mapping, fully associative mapping. This is what I'm talking about today. And lastly, the set associative mapping. Right, so in fully associative mapping, there is no fixed place for each block. That's why we say it is a mapping method where any block of a memory can be stored in any line of the cache. So to find data in this system, we say the cache compares the tag of each line to the block tag simultaneously. So because any memory block can be stored in any cache line, we say fully associative mapping offers a maximum flexibility. And this significantly reduces conflict misses and results in a higher hit rate. So however, this flexibility comes at a cost. So here we say it requires a complex and expensive hardware, including the multiple comparators for parallel tag matching. So as the cache size increases, the system slows down due to the number of comparisons required.
It's quite different in how it places data, and you will see how it compares in terms of speed and simplicity. Now, what then is direct mapping? In direct mapping, each block of memory is mapped to only one specific line in the cache. There is a fixed location for each block. This makes the system very simple and fast because the CPU always knows exactly where to look. The memory address is split into three parts, which is a tag to identify the block, a line number or index to select the cache line, and an offset to point to the data within the block. The downside is if two blocks map to the same line, they keep replacing each other, causing what's called conflict misses. How direct mapping works. Here's how the mapping is calculated. We use the formula slash text cache line equals slash text block address, all in brackets, slash mode text number of cache lines, all in brackets. This means each block is assigned to exactly one line based on its address. It's efficient because the CPU doesn't need to search all lines, just one. However, if multiple blocks map to the same line, they will collide even if other cache lines are unused. This is the main drawback of direct mapping. Visual diagram. You can see how different blocks from main memory are mapped to specific cache lines. Each arrow shows a fixed destination where the CPU accesses a block. It goes directly to the line assigned to that block address. It only compares the tag in that line. This results in a very fast lookup. But again, if two frequently used blocks share a line, they will let's say they will constantly replace each other, causing performance drops.
A big thank you to my colleagues for detailed explanations on direct mapping and fully associative mapping. I'll explain the set associative mapping. What then is set associative mapping? It is the combination of direct mapping and fully associative mapping, or in other words, it combines the advantages of direct mapping and fully associative mapping techniques to work. How does it work then? It divides the catch into several sets which contains multiple lines. Each memory block is mapped to one specific set, and within that set, it can occupy any line. Therefore, to find data, the system only searches the specific set and not the entire cache. This flexibility helps reduces conflict misses compared to direct mapping. For example, in a four-way set associative cache, each set has 4 lines, allowing 4 different blocks to coexist between or in the set. Also, visual diagrams are diagrams that shows how memory blocks are assigned to specific sets. And some advantages of set associative mapping is that it is faster than the fully associative mapping because the entire cache is not searched. Also, by allowing multiple blocks to map to the same sets, conflict misses are reduced. And in summary, we said the set associative mapping combines both the direct mapping and fully associative mapping to work. And it works by dividing a cache into several sets containing multiple lines, and each memory block is mapped to one specific set, and within that set it can occupy any line. Thank you.
Yeah. Hello, sir. Please, my name is Christian Nyan Asar, and I'm here to represent on associative memory and bank memory. Associative memory. Associative memory, also known as content addressable memory, retrieves data based on content rather than a specific addresses. It's typically used in fully associative caches where the system checks all caches lines in parallel to find a match. This makes data retrieval extremely fast, but the hardcore requires is costly and complex. So it's mostly used in small and high speed applications. We move on to slide 3 and what is banked memory? To explain further, banked memory splits memory into multiple independent banks. Each bank can be accessed simultaneously, allowing and reducing memory latencies. This approach is commonly used in multi-core processors, GPUs, and other parallel computer systems to improve memory throughput and support faster executions. And we move on to slide 4, and that's visual diagram. Yeah, visual diagram. And to explain further, in this concept on the left, we show associative memory where content is matched across multiple lines simultaneously. On the right, bank memory allows different memory banks to be accessed in parallel. Together, these techniques help systems respond faster and scale more efficiently with complex workloads.
Hello everyone, I'm here presenting on effects of hit ratio on average access time. This concept is essential for understanding how fast or slow a computer system retrieves data from memory. in computer systems, memory access speed greatly affects performance. To make things faster, we use cache memory, which stores frequently used data. When the CPU looks for data, if it finds in the cache, it's called a hit. If it doesn't find it, it's a miss here. And the system has to access slower main memory instead. What then is hit ratio? Hit ratio tells us how often the system finds data in the cache. We calculate it by dividing the number of hits by total number of memory access. It usually has a percentage, for example, a 90% hit ratio in 9 out of 10 times. The data is found in the cache. A higher hit ratio means the system is faster and more efficient. Slide 4. What is average access time? Next, we have average access time, or A8. It's the average time the system takes to access any data, whether it's from cache or memory. Relationship between hit ratio and A8. The relationship is simple. When the hit ratio goes up, the average access time goes down because most data is retrieved from the fast cache. When the hit ratio goes down, more time is spent accessing slower memory, so performance suffers. I'm the final speaker of our group. My name is Tifle Sankra, and I'm presenting on how cache works within a virtual memory system. This topic ties together everything we've covered so far, showing how cache memory interacts with address translation to improve speed and efficiency in modern computers. Let's start with a quick look at virtual memory. Virtual memory gives each program its own virtual address space, which makes it appear as though the system has more memory than it physically does. Behind the scenes, the Memory Management Unit, or MMU, translates these virtual addresses into physical addresses. This allows the CPU to run large or multiple programs efficiently, even when RAM is limited, which is then managed by memory management. Role of cache in virtual memory. Now, where does cache come in? Cache, sorry, let's start with a quick look. Where does cache come in? Cache is a small, high-speed memory that stores frequently accessed data to avoid the delay of fetching it from the main memory. However, in virtual memory system, the CPU uses virtual addresses while the cache uses physical addresses. So the system must translate the virtual address before accessing the cache. To speed this up, we use a translation to speed this up. To speed this up, we use a translation look side, what do we call it? Translation look side buffer, yeah, or what we call a TLB, which catches recent addresses translations. This reduces the time spent converting virtual addresses into physical ones before checking on cache. Yes, thank you for your attention, and that concludes our group presentation for Group 7. Thank you very much.